is Julien Ah-Pine. I'm an associate professor from the University of Lyon. And today I'm going to talk about a general framework for comparing heterogeneous binary relations. So here is the outline of my talk. I will start by introducing basic definitions about binary relations in general, and I will also introduce the problem that I will try to deal with in this talk. So typically, I want to measure the similarity between two binary relations. Okay. So one way to do that in the statistical literature is to use Kendall's general coefficient, gamma. So I will recall this similarity index. And then I will present a kind of generalization of this coefficient. So the first contribution to this end is to give another interpretation of Kendall's gamma, which uses rational matrices that has been introduced in the previous talks. Okay, so and then the second contribution will consist in extending Kendall's gamma in order to better treat heterogeneous binary relations. Okay, so in that case, I will embed the measure in an Euclidean space and show you how we can, in particular, treat heterogeneous binary relations. Then I will give you a numerical example of the kind of output that this framework is, and I will conclude and give you some future works. Okay, so very rapidly, binary relation R over a finite set A is typically a subset of the Cartesian product, so it's a set of pairs of items. Okay, if Ij belongs to R, we say that I is in relation with J for R, and this is also denoted I or J. Okay, so I am interested in well-known binary relations, okay, equivalence relations, so they are reflexive, symmetric, and positive binary relations, and also order relations. So we have different types of order relations, depending whether we have missing values or ties. But typically we can make the difference between pre-orders, partial orders, and total orders. So these are the basics about binary relations, so I won't spend a lot of time on this. But just to give you an illustration of the idea, equivalence relations, they are related to qualitative variables. Okay, so here is an example. If I take the small x as the variable of color of eyes over 5 different items, okay, brown, blue, green. So this is a variable of measurement made of qualitative information, and it infers an equivalence relation. And an equivalence relation, it's a set of pairs. It's similar as graphs. Okay, they are particular graphs, but they are typical graphs. And we can represent graphs by adjacency matrices. So this is an example of adjacency matrix. So typically, given the small x, okay, we have the definition of the the adjacency matrix given as follows. Okay, we put 1 if I is in relation with J. Okay, for the relations rapidly, so there is a second example. So they are related to quantitative variables. Okay, so here x represents the ranking of items. Okay, so A, for example, is ranked first, and we have the same definition here. Okay, to go from the small x, a variable of measurement, to the adjacency matrix. Okay, so here is the adjacency matrix related to this quantitative variable. So, in the context of this work, we suppose that we're given two variables of measurements, okay, and they are both kinds. I mean, x and y are both qualitative, or x and y are both quantitative. So the problem that we would like to address is how can we measure the proximity between the binary relations underlying the two variables. And in particular, I will focus in the second part of this talk on heterogeneity. So what I mean by heterogeneous binary relation is, for equivalence relation, for example, it's when we have two variables which have two distinct number of categories, or they have two different kinds of distribution. Okay? And for order relations, so I said previously that there are different kinds So when x and y are two order relations but of two different kinds, how can we measure the similarity between x and y? So I will recall now Kendall's general coefficient. So we are given x and y, and Kendall's introduced a general correlation coefficient, which he named gamma, and the general formulation of this coefficient is given here. Okay, so we are given x and y, and here we have these two straight x and straight y, which are two square matrices which are derived from x and y. Okay, so it's a general formulation, and depending on the way we derive straight x from x, we have a particular association measure. So this general formulation actually embeds many association measures. So here are rapidly two examples. As for equivalence relation, okay, so we can see that, and it is Bejevius and Johnson who proved those results. So typically using gamma, we can have, if we define straight x like this, the Chuprow's T coefficient, which is related to the chi-square coefficient. And we'll have also the G index, which is the Johnson and Bejevius criterion that we talked about in the previous talk. Okay, so this is the Johnson-Bejevius coefficient. And the main idea here is to show that this general coefficient allows defining different types of association measures. So I won't go into the details of the definition of the different criteria. So this was for equivalence relations, and for other relations, obviously we have Kendall's two coefficient, which is given by this uniform distribution, and we have also Spearman's rho, which can be obtained as a particular case of Kendall's gamma. Okay, so I have recalled the work of Kendall's, which can be used to measure the similarity between equivalence relations and order relations. So now I'm going to present another view of this formula. To do so, I will talk a little bit about relational matrices. Then I will reinterpret Kendall's gamma in terms of relational matrices. And then I will show that this formulation is based on what I call weighted indeterminacy deviation principle, and which actually is similar as the indetermination situation that we talked about in the first talk. Okay, so I showed that binary relations, since they are set of pairs, they are graphs and they can be represented by adjacency matrices. But since we're dealing with binary relations, those types of relational data, they satisfy different properties, and because of those properties, they were called by Marco Tortino as relational matrices. So, just rapidly, here is a main property of relational matrices. We know that binary relations, they are defined by different relational properties. Okay, and we have the property that the relational matrix, okay, the identity matrix, they allows modeling the relational properties as linear constraints. Okay, so I won't go into the details, but this is one reason why I will call relational matrix adjacency matrix in the rest of the slides. There have been several works about using relational matrices to reformulate association measures. So this series of works was to have a better understanding of the differences between the different coefficients. But here is a list, a partial list of previous works on this topic. So in this work, I propose to reinterpret Kendall's gamma in terms of relational matrices, but based on a concept which is the weighted indeterminacy deviation principle. So when I say indeterminacy, it's another translation for indetermination, but it's basically the same concept. So to introduce all those concepts, I will start by giving the definition of the opposite of an equivalent solution or an order relation. Then I will give the formulation of a new kind of interpretation of Kendall's gamma that I call lambda. Okay? And we will see that it can be expressed in terms of rational matrices of opposites of the binary relations, and weighting schemes. Then I will show that this lambda, of course, generalizes over particular association coefficients. And then I will give some more details about the weighted interluminosity deviation principle. So, the opposite relation of